So I hope you have enough attention left, because we've got Divyan and Verosha that are going to speak to us about creating personalized images with Python's Stable Diffusion. Over to you.
Okay, cool. I hope everybody can hear me loud enough. Okay, thanks. Okay, so hi everyone. Like mentioned, I'm Verosha, and that's Divyan sitting down. He'll come up later in the presentation. But just before we start, a little about us. We both have our master's degrees in computer science. We currently work at Melio AI. Melio AI is a company that focuses on developing and deploying ML solutions. Now, today, we're very excited to share our explorations with Stable Diffusion in Python, and we're hoping by the end of the talk, we spark some curiosity around generative AI. Now, a quick heads up, prepare yourselves for a lot of cringy photos that you're about to see. So these are some of the model's output images and some foreshadowing apparently of what we're gonna look like in our old age. And yeah, one last thing. I'm recovering from a flu, so just bear with me if my voice is a bit raspy or if I just need a cough. Okay, cool. So before we begin, we'd like to take a moment to highlight the key learning objectives that we're going to be covering in the slides. Okay, so we're going to start off with a high-level overview of Stable Diffusion, what it is, how does it work. And this will ensure that we're all on the same page. So whether you're already familiar with Stable Diffusion or you're just getting introduced, we'll ensure that everybody's comfortable with the topic. Next, we want to move on to how you can train your own Stable Diffusion model and run prompt inference to create custom images. And finally, we'll wrap up by discussing the ethical and licensing considerations when working with these powerful models. Okay, so let's start with the basics. What is Stable Diffusion? Now, Stable Diffusion is an exciting type of generative model that specializes in creating images from textual descriptions, also known as prompts. And it uses a deep learning architecture that focuses on the diffusion process. Now, this process helps refine random noise into clear, coherent images step by step. Some of the key concepts central to Stable Diffusion include text-to-image capabilities, the diffusion process, like we mentioned, that transforms random noise into clear, refined images, and the notion of latent space. Now, we'll touch on latent space a little later, but for now, all you need to know, it's crucial for the model's ability to understand and generate images. Now, Stable Diffusion is open source. There's various models available on Hugging Face, and it allows you to customize the model for your specific needs. Okay, now that we've covered Stable Diffusion at a high level overview, we want to dive a little deeper into the mechanics of how Stable Diffusion actually generates an image. Now, Stable Diffusion starts by transforming a text prompt into a numerical representation that effectively summarizes your text input. So you would see in the first block, we have our prompt as Spider-Man in space. Now, by using this image representation, instead of generating high-resolution images directly, the model enhances computational efficiency. The entire process starts with random noise, and it's refined over multiple time steps, as you'll notice with the pink looping arrow. And this results in a high-quality image that closely aligns with the original text prompt. Now, for the next slide, we want to zoom in a little further into the actual diffusion process and understand how Stable Diffusion derived its name. Okay, now in this diagram, there's a lot of information that's happening. So we're going to break it down into the key focus areas throughout these slides. Okay, so starting with the first block, the process begins with an original image in pixel space. The image is then passed through an image encoder, which transforms the pixel data into a latent representation. The encoder captures the essential features, so say colors, shapes, and textures, and it allows for more compact and efficient representation in your latent space. Okay, now moving to the second block. So we're in the latent space now. So what is latent space? Well, you can think of latent space as a compressed hidden version of data. In our case, we're working with images. So instead of representing the image in pixel form, it's transformed into a more compact form with just the key features that the model needs to understand. Now, in the latent space, there's a process known as forward diffusion, which is applied gradually to keep adding noise to the latent representation of the image. Now, Stable Diffusion uses a diffusion model called the latent diffusion model. And it's made up of 3 parts, and we're going to touch on that throughout these slides. Now, the first part is a variational autoencoder, and simply it just encodes the image from pixel form into the latent space. Now, keeping within the latent space, we've also got another process known as reverse diffusion. And basically, in this process, it progressively removes the noise that was added during your forward diffusion. And this denoising process is crucial for generating those refined images that we spoke about. Now, we mentioned in the previous slide that the latent diffusion model has 3 parts. The second part to this is your unit, and basically it's used to denoise your output image. Okay, moving on to the next block. Finally, the third part of the latent diffusion model is your decoder. And this is used to convert that latent representation of the image into that coherent, refined image. Okay, then just taking your attention to the conditioning block. Now, throughout the process, the model leverages a text encoder that translates prompts into a semantic map. This mapping helps guide the image generation process by linking the latent representation back to the desired concepts or features that were mentioned in the prompt. Now, the semantic map basically ensures that the generated images align with the user's prompt. Now, hopefully all of the slides that we've covered so far provided you guys with a high level or a detailed explanation of how Stable Diffusion works. And in the next slide, we just want to touch on why we use Python for this task. So at a high level, we want to cover the core libraries that we're working with and how we're leveraging Hugging Face for our models. Okay, so really quickly, Python offers a vast range of well-documented libraries and tools that make working with images and training your models much simpler. For deep learning frameworks, Stable Diffusion can be implemented in TensorFlow or PyTorch. In our case, we made use of PyTorch, and you'll see that later in the training. Now, sometimes you may want to manipulate your input to output data to create visualizations and find some insights in your data. Now, for that, we made extensive use of Jupyter Notebooks and cloud compute resources, so AWS. And yeah, finally, when it comes to accessing pre-trained models, Hugging Face Hub provides a wide range of open source machine learning models. Okay, so on this slide, we just want to touch, and I'll be quick here, just the core libraries that we used. So starting things off with PyTorch, this served as the underlying deep learning framework for us. It leverages CUDA for GPU acceleration. We also made use of it for to manage cache memory and for our notebooks during training. And finally, it helped facilitate inference. Next, we have the Pillow imaging library. And basically, this was just used for pre-processing of our training images and normalizing our classes, our class images. And yeah, finally, the diffusers library. And basically, this was the backbone of the Stable Diffusion process. The library itself contains a lot of documentation on the tools and techniques and how you can get started with training your own Stable Diffusion model. Okay, so we just want to quickly go through the diffusers library. Okay, so with the diffusers library from Hugging Face, it's made up of 3 components: your diffusion pipelines, your noise schedulers, and your pre-trained models. Now, you might start to recall some of these points covered in the Stable Diffusion explanation that we did earlier. And you're going to see it come up again when we run through the training portion. Okay, so going through pipelines basically offers an easy way to run your diffusion models for inference by combining all of the necessary components, such as your multiple trained models, your schedulers, and your processes into a single end-to-end class. It's flexible, so it allows you to adapt different schedulers, or model components as you need. Sorry. Okay, next, moving to your noise schedulers. So basically, your noise scheduler takes a model's output and time step, and it's used to produce a denoised image. Now, depending on the context, it defines how to iteratively add noise to an image or update a sample based on the model's output. So in the case of training, a scheduler adds noise to the sample to train the diffusion model. While for inference, it determines how to update a sample using the output from a pre-trained model. And lastly, we have the pre-trained models. Now, the diffusers library does offer ready-to-use trained models with popular algorithms, and it makes it very easy for you to get started. Okay, so with our not so short overview of Stable Diffusion and the various Python libraries in mind, I'm going to hand over to Divyan, who's going to walk you guys through how to train your Stable Diffusion model. So you'll get to see the code and some of those generated images. He's going to take you through prompt considerations and finally address the ethical considerations that we should all keep in mind. So yeah.
Can you guys hear me? Okay, it's fine. Let me just put this in my pocket. Cool. Yeah, thanks, Verosha, for that introduction. We thought it's interesting to actually cover just a little bit of theory before going into the Python libraries, well, the diffusers library. Nowadays, a lot of these libraries are so easy to implement. It becomes easy to overlook how these processes actually work. So that's sort of why we wanted to cover some of that theory. So yeah, without further ado, we'll jump straight into what the code is for what Verosha actually spoke about. Before we do this, we thought it might be cool to just jump right to the end first and take a look at what we actually produce. So on the left, you can see some training images of Verosha and I. The images we used for her model was more or less non-intentional images for training. So images you might just find randomly in your gallery or online, social media, and so on. The images of myself, we set up with a tripod and tried to make it as intentional as possible for training a model. But as you can see that in both cases, the model was quite resilient to a lot of the variations we put it through. So yeah, it really doesn't matter the type of images you put in, as long as it can see your face. It'll of course do a little bit better if more features of your face is available. But as you can see, that sort of looks like me. So yeah, So we can dive into the code. Of course, we could show you this entire notebook, but it might be very difficult to follow. So we broke it down into components, and we'll be looking at it in this order. A lot of the notebooks you might find online will have these core code aspects in them. So jumping to the first one, setting up your environment. Firstly, so we used a Jupyter notebook. It's just easier to explore on. The first thing you need to do is make sure you're using a GPU. You can train it on a CPU. It'll probably take over a year. So a GPU, much better. In our case, we used a 24 gig video memory GPU, and that sort of served the purpose. You could get away with a smaller GPU. It just depends on your input images, and we'll cover that later on. The next step is some dependencies. Now, again, you don't need to pay attention to all the code. The main one is this red arrow that we have there. That's where we pop installing the diffusers library from the Hugging Face website. There's a few other dependencies we're installing. Now, the Hugging Face website is actually very, very well documented. You'll not only get different ways of installing your diffusers library, but you'll get a lot of the dependencies you need as well. So for our case, we just set up a quick method. So for any notebook we're running, we just run this one method and we get started off it. So next is some config setup. So we pulled our diffusers library and installed it. We're going to set up some config. Starting from the top, you'll see that we're defining a few variables. One is the class. So the class is sort of the type of input you're trying to train your model on. In this case, it can either be man or woman, right? And you'll see how this comes into play a little later on. So we're setting the class to woman. The model name. Now, Hugging Face has a lot of different models. I think it's over like 45 models. In this case, we're using one called Dreamlike Photoreal, and this produces hyper-realistic images, like you've seen from the example. So we're just defining that. We're also defining a random token. Now, your token is very important because the diffusion process associates your training images with a token. So when you run inference on it and you give it a prompt, you actually give it the token, so it knows the training images to look for. And it needs to be very random. For example, if my name is Brad Pitt, and I use Brad Pitt, and I train the model, and then I say, generate a picture of Brad Pitt doing a presentation, it's probably not going to generate me, even though I provided that training images, it's going to generate the famous Brad Pitt. So in this case, something completely random. Context name, that's just something we set up for directory structure, just so we know the person that we are dealing with here, so Verosha Pillay. And we'll touch on regularization in a bit. And you see we have some code in the if statement. This is same for woman. We just have the man there, for example. We're generating a concepts list. And this, again, is documented by Hugging Face. And this just takes in all of the variables we set up. One thing you might notice is that towards the bottom of that, we're setting a regularization file. So if man, it's using a man regularization file. So what really is that? Regularization helps prevent your model from overfitting. So if I'm training my model on images of myself, I want to also incorporate some variations of hairstyles and dress styles. So I want to include some regularization. And yeah, so I'm just including that file. And you may wonder, okay, cool. So maybe this file is stored locally. Where does this file come from? In the next block of code here, you can see, again, the small piece of code in the top. We're just running a wget from Hugging Face datasets already, and it's just pulling a regularization file, which we defined earlier. And you can see it might be a little bit blurry, but Hugging Face has a bunch of predefined regularization zip files with images in them. So again, completely easy to use this and incorporate into your training. If you just look into this regularization file just a little bit, you'll see that this is what it looks like, right? And this, of course, it's meant to prevent overfitting and provide some variation. But through some iterative testing, what we notice is because of the nature of these images, it looks some like oil painting and some very abstract images, it actually performs a little bit worse. So what we did was taking in the learnings from actually using a regularization set of images, we just straight off of Google Images, we created our own data set of around 200 images to closely align what we are trying to run inference on. So we took pictures of casual dressed men and women or using some formal clothing because that's what we wanted to run inference on. So it not only prevents overfitting, but we're also giving it data that we actually want the model to know. Yeah, so again, the last step here now in data set preparation, we want to pre-process our training images. So I have a bunch of images of myself, Verosha as well. And these are taken from our phone, which is various different resolutions and some very high quality and size. If you put this in a model, it's actually going to run out of memory. It's going to be very difficult to train. So we just have this small method called process image, which we created, and it takes in a target size. In this case, we set it to 512 by 512. And this simply pre-processes our training images and normalizes them to a set size. And that's the only thing this method is doing. So regardless of whether you're cropping images in different rectangles, it's just going to make it 512 by 512, and it's going to help the model to train quicker. Now we'll move on to model loading and training, and you'll notice I highlighted both these blocks here because they actually happen more or less at the same time. So looking at the first piece of code there where we're saying Python 3 train Dreamboot. So we're calling a script called train Dreamboot. And I know now Dreamboot is like a new keyword I'm using. I'll explain what that script is. But the point is we're sending it in some parameters. In that first block of code, you can see we're sending in a pre-trained model name. So that's just an example of how we're calling the script with it, but all the parameters are actually listed here in this method. You may remember the model name we defined it. We defined it during our config. It was the dreamlike model. The second red arrow, which is pre-trained VAE, you may remember that from Verosha's portion. That's the variational autoencoder. So that's what's used to iteratively add and remove noise from the image. And that's what helps the model learn. So you may realize that we're training a model, but there's actually two models that we're defining. A pre-trained model, which is going to do the inference, but we also have a variational autoencoder model that helps add and remove noise. And that's where the theory actually helps you understand why you're actually doing this. And these models are in Hugging Face. You can choose anyone. We use stability. Again, there's a lot of default parameters which we set. The third arrow is the resolution. We're just aligning that to our training images. And then going all the way down to the last arrow, the max training step, we're just capping it to 1,000. A lot of these variables are actually predefined. So straight from the documentation, you can use it as is. Probably just the training steps and the class images, like we have it as 200 there. It's just depending on what you're trying to do, you can change that. Otherwise, it actually works perfectly using the default documentation. So now that we have these parameters and we're sending it into this train Dreamboot script. What really is a script? Because we haven't spoken about it. What is Dreamboot? So this is a screenshot from Hugging Face's website. So on the Diffusers website, you'll see it talks about Dreamboot. And we'll read that first portion that I highlighted in red together. Dreamboot is a training technique that updates the entire diffusion model by training just a few images. It works by associating a special word in the prompt with the example images. So again, you can just see that it's associating your training images and your token, and that's where our token comes in. And Dreamboot is just a process to update our pre-trained model. So Dreamboot takes in your pre-trained model. It takes in your variational autoencoder and your pre-trained images. And when it actually does this training, it helps convey that training to your pre-trained model. So now it knows, okay, this token is of this new subject. Cool. So we spoke about our parameters and what script we're calling. And now we call our train Dreamboot script. The first thing you'll see is caching latents. And it'll go ahead and cache all 200 of your class images. So depending how many regularization images there are, it'll start to cache those into memory. And then if your logging is on, you'll see some of your parameters. So there's number of examples, 200, and the batches and the epochs that you're running for. Once it's done caching these latents, the next thing you should see is that the training actually starts. So just past the progress bar, you'll see it goes from out of 1,000 steps all the way down where it's 100%. So this is 1,000 out of 1,000 training steps which we're doing. So on I believe it was a 24 gig video memory GPU instance, training a model for myself and for Verosha took around 13 minutes, which isn't bad at all, considering the quality of output that you can get. Cool. So when your training is done, and of course, depending on your output path that you sent in during the train reboot step, you will have a folder with weights. And that weights currently it's not usable as yet. So often when you're creating your models, you want to create a checkpoint after you have your weights from training. And that's what this method is doing. Again, you'll see that in the command script here, we're using a script called convert diffusers to original stable diffusion. That's a script that also exists on the Hugging Face website. So this script knows how to convert those weights into a callable method or callable model, sorry. So yeah, you can run this and you'll have a checkpoint file created. Yeah, cool. So now that we have our checkpoint created, the last step is to load your model and run inference. So there's a few things you need to set up before you load your model. So here we're just setting up some parameters and variables. The first one is your prompt. So we'll touch a little bit about like the advantages and disadvantages of different types of prompts. But you do want a sort of detailed prompt. You can say, okay, your token wearing a suit, that should be fine. But you're going to leave a lot up to the model to imagine. Like you're wearing a suit of what color, what are you doing? Are you sitting? Are you standing? Are you outside? Is the environment lit or not? So you kind of want to guide your model as much as possible to a specific resolution. And of course, again, you can't have too large of a prompt, and we'll speak about why later. The second variable here is negative prompt. So commonly when you're generating images of people, common negative prompts is anything dealing with bad anatomy. So you want to try and remove that. And a lot of times, and I think we have some examples where you'll see images of me with like 7 fingers on one hand. And how you get around this is you send the model a negative prompt. And if you just read a few of that, it's duplicate, bad anatomy, extra legs, so on and so forth. And online, you'll come across a lot of negative prompts for different types of classes that you're trying to generate. And then, yeah, a few of the latter variables we're setting here. We'll look at guidance scale. So the third one here from the bottom. Guidance scale tells the model how specific or how closely it needs to follow your prompt. So you can imagine a higher guidance scale means follow it very, very carefully. A lower guidance scale is trying to tell a model you can be a little bit creative. So we found 7 to be a sweet spot. Yeah, so again, we're just saying the width and height. So that's just from our training input and where to save the images. Lastly, we're going to load our model. Now that we have our model checkpoint saved, we're just going to use a stable diffusion pipelines, which Verosha spoke about. We're going to specify our scheduler. A scheduler helps to move from a non-noisy image, from a noisy image to a non-noisy image. That's your inference. And lastly, this bottom block of code, again, all of this is documented. This uses torch in inference mode, and we're sending in all of that input parameters that we have through the pipeline, which is our model which we created. And you should see something like this, right? So you'll have an output image, which is pretty cool. Maybe it matches your description, maybe not. Something maybe you can't read from the top, but what it actually is telling me there, that small text, is that the prompt got clipped. Clipped meaning that your input prompt, not all of it got sent to the model. And yeah, you should always have logging on when you're doing these type of things, because your input model, in most cases, well, in this case, the Stable Diffusion model, takes in 77 tokens, which is 77 different words. Anything more than that gets clipped. So you'll never know what the model's actually not taking. So you need to have logging on to actually be aware of that. Maybe you need to shorten your prompt. Yeah, then here's just me in a suit around my 50s, and yeah, in a Formula One suit. Of course, there's not a lot of guidance given there, so I try to imagine things. It may have done it wrong. And you can see with the intentional images I took, it kind of generated my face pretty accurately. And we'll skip through to Verosha's images. Again, very similar, her in her 20s and then at older ages. And yeah, the face from the 20s also looks very accurate. And this speaks again to the resiliency of the model actually picking up useful features. And then, yeah, so we'll talk about some of the pitfalls really quickly before time. So first is unclear prompts, and this is something I spoke about. You want your prompts to actually guide the model just a little bit for it to help it get to where it needs to. Moving to the second one, overloading. At the same time, you can't give the model too long prompts. It's going to clip the prompt up, and it's not going to be able to generate an image taking in all of the information you're giving. And if you don't have logging on, you'll never know what portion of your prompt is getting clipped. Inconsistent outputs is a third. So even if you set a seed during your inference, if you generate an image that looks cool and maybe you want to change the color of your shirt, you'll never get the same image again. The shirt may change, but that image is like, it's very difficult, if not impossible, to get the exact same image. So a suggestion here is to always save every generation you make, whether it's good or bad, just default pipeline, save it. And lastly, training data. So it really depends. The test version I did, hers had a lot of variation. Mine was very specific, and the model still trained well. This might be due to the dreamlike model which you use. Maybe it was a really good one, but you really want to have some variation in your facial features. That's most important. And then moving to the last slide, legal and licensing consideration, and this is an important one to end on. On the right-hand side of this presentation is the license from the dreamlike model we use straight from the Hugging Face site. We just summarize what it said here. And you'll notice a lot of this is very tightly licensed. Open source doesn't mean you can do anything you want. For example, it'll say you can use it for commercial purposes only in teams less than 10, which is already a problem for a lot of us. The authors claim no rights over your outputs. And if you're using the model anywhere, you need to give it the full name, the link to the website, the link to the license. And a lot of the cases, even the other models we looked at, one of the first things is if you're going to use the model, you need to email the developers and tell them what you're using it for. So yeah, that actually brings us to the end of our presentation. We have like a moving slide of different images that we have of us. And we hope that through the theory and the practical portion of this, you learned how Stable Diffusion works, but also actually how easy it is to implement straight just from good documentation from Hugging Face.
Thank you very much. Do we have any questions for Divyan and Verosha?
Hi guys, thank you very much. That was really, I knew nothing and now I feel like I know something. I'm just tying this together with the talk earlier on about Langfuse. While you guys were putting this together, did you encounter any sort of evaluation sort of frameworks? Like how do we tell that an image is good enough? Is it kind of like you know it when you see it, or is there like are there quantitative methods there?
Yeah, I think that's a good question. And we actually had this conversation as well. Most of the time, you probably want a human in the loop. A lot of the models actually have, so on Hugging Face, you may see a model has an NSFW filter. Some may not. It'll be like a big warning. There's no filter on this. And I think so that's actually a telltale that there is a way to evaluate this. Second thing is that when we use SageMaker, AWS SageMaker, and our notebook was sitting there. And when we generated a few images, and it may just be like me in board shots on the beach, SageMaker, the notebook actually stopped it from showing me this image. It said it couldn't show me this content. So to answer your question, there's definitely a way to evaluate this. We haven't taken a look at it, but if AWS is doing that to prevent something from showing, yeah, there's probably a way. For us, though, we just use human in the loop to decide what's good and what's not. And these are like the decent ones we should be showing. Yeah. After you.
Thank you. Thank you both for the talk and for persevering through the cold. The flu, that is, not the weather. I was going to say the mere fact that I, with no background to this, feel confident, like, oh, I could do this, probably means you've explained this extremely well and it's rather difficult. And second, not to pick on something specifically small that you mentioned, but during your run through of the libraries that you used, you mentioned PyTorch, and maybe you unknowingly mentioned it specifically manages cache. So as someone from the engineering side of this kind of thing, is caching a concern for you? Is it, do you need to keep things kind of nearby to frequently update your results or something like that?
So that actually became a big thing. What we noticed was, so we had this one notebook, 24 gigs memory, and we're just using it to train models. We trained one model on Verosha, we did some inference, and it was working well. And then I started training on my model, and it just kept like breaking and restarting, and we didn't know why. And then we did some research, and PyTorch actually has this one line called torch the clear cache. Literally that's it. And we ran it, and on the notebook you'll see the kernel memory just like go all the way to 0. And then we run our training again, and it works. And we felt that wasn't really covered in the documentation, because maybe the companies using this have very large instances. We just went from CPU, which of course didn't work, to 8 gigs to 24 gigs, just to have to try and be cost effective as well. So we indirectly came across that cache actually does play a role, and somehow these models are being cached when you're training. So just in your training script, before we said change reboot, we just have one line that says clear cache. That's it. And yeah, it was sweet magic after that.
Hi, and thank you again. That was quite interesting. I saw that a lot of Verosha's photos had that little bit of a washed out look, because I think two of her training photos had that look to it. If you have more varied photos, would you get some of them with that washed out look, or would it be more of a average?
So are you speaking like the washed out look over the entire
A
image?
little bit overlit on the face.
Okay. Yeah, so I think maybe that's a good observation. Maybe we haven't spotted that. One thing we did note is that what this model actually is good at is picking up features. And despite the washed out looks of the input images, the fact that not all images have this washed out look, during training, the model won't recognize it as an important feature, and it'll actually miss it out. Whereas all this feature has 2 eyes, the model will be like, okay, 2 eyes and a nose. The model won't be specific to clothing. Clothing's different. So I think to your point, maybe if all the input images are washed out, the model may start to think, hey, okay, Verosha needs to look a little bit washed out. But yeah, it could be an interesting thing to check if more of the data set. But just to cover that, these are 4 of the 13 images we used during training. So yeah, just 4 random ones.
Just a follow-up question. I would have thought that normal number of arms and legs would be kind of a given. Are there any cases where you don't have to specify that as a negative prompt?
So no, I think so. The model always takes in a negative prompt, so you can choose to run the risk. I think in a lot of cases, so there's a few we generated of some other of our employees, and one was of her holding a mic, and just doing that had 6 fingers on it, and like you had to just look at it to see, okay, there's 6. Maybe the model can't differentiate like the shadows that's going on and actually count what's happening. But I think in general, yeah, this negative prompt, it's because it's an input and like it's very highly documented as one of the limitations, but also an advantage that you can completely stop the model from going down the wrong road. Yeah, I think it's important to have it there. I think maybe it's worth doing like a test of no negative prompts and negative prompts just to see actually the impact it has. That's a good question.
Thank you. Any other questions?
Hi, I was just wondering, I think you said you trained the model for 13 minutes. Did you try like running it for longer or shorter? And did you see a change in the output, or was it pretty good by that point and wasn't worth going for longer?
Yeah, so the first, like I said, like we started on a CPU first, didn't work out, and then we went to 24 gig memory. And in general, the Hugging Face website suggests you need up to 6 images. And we thought, okay, that's pretty crazy. 6 is a very little amount of images. So we chose about 10 to 13 images. The training took 13 minutes. And the reason we know that is because we wanted to check it against costing on our AWS instance. So 13 minutes with 1,000 epochs, and that's default documentation like numbers. It actually produced results where we didn't feel like you needed to retrain. So what we just did was, once the weights were done, we created a checkpoint, pushed it to our cloud storage, so S3 bucket. And anytime we needed to run inference, we just plugged it to a SageMaker endpoint. I think, yeah, there was nothing glaringly like bad with our inference where we were like, yeah, maybe we need to investigate this washed out effect. Maybe it's the training, maybe the resolution of 512 is not good. But no, we didn't really need to go back. Yeah, 1,000 steps was good enough.
Okay, last question.
Sorry, I was just kind of curious. What was the cost implications of creating like something this small scale?
So in terms of like developing it, like obviously it took a while to sew things together. Libraries change so quick. So to do this, it took some time to actually put like this all these ideas together. But to answer your question specific, I assume you're talking about training, like the cost of training. The cost of training for 13 minutes on I believe it was a ML G4DN AWS instance, took around $5. So it can get a little bit complicated because we use images that are 512. We use 200 regularization images, so we didn't do a lot of caching there. Yeah, so there's a lot of input parameters which you could tweak, like from the previous question, but just with the parameters we had, it was around like $6. Yeah.
Okay, let's thank our speakers one more time.